Section 1 of the ZAERO Advanced Training Theoretical Background of ASE. So the outline here for the aero-servo-elastic modeling in ZAERO, we have a state space time domain approach via the rational function approximation. We have a frequency domain approach which does not involve the rational function approximation. We have control system augmentation, which allows for actuator and sensor modeling, the modeling of control elements, and then you can output the ASE plant, vehicle, and closed loop system plant models. Additionally, in ZAERO, you can perform a stability and performance analysis, which includes the VG and VF diagram output. You can also perform a gain margin and phase margin analysis and output the Bode diagrams. And then ZAERO will perform the minimum singular value for the multi-input, multi-output systems. And then we'll finish off this section with a numerical example. The aero-servoelastic models in ZAERO are described here on this slide. The ASE model consists of the aero-elastic model, which specifies the dynamics of the system depending on the structural masses, stiffness, damping, and unsteady aerodynamic forces. Then you add on top of that the actuator models, which specify the actuator dynamics and inputs of the ASE model. You also can specify sensor models, which specify the outputs of the ASE model. And then finally, you can optionally specify control system models for feedback control. The frequency domain and the state space ASE approaches can be selected using the ASE module. The frequency domain approach incorporates the transcendental generalized aerodynamic forces, the GAFs, QHH, QHC, and QHG. These are all discrete matrices which are functions of IK, the reduced frequency. This approach results in an exact solution for the applied aerodynamic matrices. However, it cannot lead to the standard state space equations. Next, the state space approach is built using the rational function approximation of those GAFs. This enables the ASE state space models to be constructed and the time domain analysis and simulation to be performed. The QHH of IK is the GAFs due to the structure modes, QHC is the GAFs due to control surface kinematic modes, and QHG are the GAFs due to sinusoidal gust, where of course K is the reduced frequency. So the state space approach takes these matrices, which are discrete values of frequency, and converts them to the Laplace domain where they become functions of S. So the disadvantages of the state space approach are that it involves approximation, which may introduce error. So the state space model should always be verified with the frequency domain results. So section 1.1, we'll start out talking about the ASE analysis by the state space approach. So first we'll talk about the procedure used in ZAERO to formulate the closed loop state space equation. The state space equations are formulated in the modal coordinates Cassi. The state space equations of the aeroelastic system require the rational function approximation, which transforms the frequency domain unsteady aerodynamics into the Laplace domain. The state space equations of the plant model combine the state space equations of the aeroelastic system and the actuator dynamics. So we start out here with the state space equations of the aeroelastic system. We add on the actuator dynamics, which gives the state space equations of the plant model. Now the plant model can be combined with the control system model, which gives the vehicle model. And then finally with the vehicle model, we can apply the gain matrix, which yields the closed loop state space equations. So in ZAERO, when you do a closed loop ASE analysis, it simply finds the damping and frequency by performing the eigenvalue analysis on this A bar V matrix. And then you can optionally output the ABCD matrices of either the aeroelastic model, the plant model, the vehicle model, or the closed loop model from ZAERO for further analysis outside of ZAERO, for example, in MATLAB. So we'll start out here with the Statespace approach. The equation of motion of the aeroelastic system in discrete coordinates is given by equation 1.1 here, where MHH, CHH, and KHH are the generalized mass damping and stiffness matrices, and the subscript H denotes the number of structural natural modes. MHC is phi H transpose times MGG times phi C. This is the generalized control coupling mass matrix, where phi H is the mode shape matrix, usually obtained by Nastran or your FEM solver, which contains the natural modes. MGG is the G-set mass matrix, and phi C is the kinematic control surface modes, where the subscript C denotes the number of control surfaces. Next, we have C and delta, which are the generalized modal coordinates and the control surface deflections. Q infinity, of course, is the dynamic pressure. And QHH of IK and QHC of IK are the generalized aerodynamic force matrices due to the structure modes and control surface modes. They are computed as shown in equation 1.2. So we have the AIC matrix, which is computed by ZAERO, pre and post multiplied by the spline matrix G. QHH is pre and post multiplied by phi H, and then QHC is phi H transpose on the beginning, and then phi C on the end here. The major technical issue involved in forming the state space equations of the aeroelastic system is that the GAF matrices are computed in the frequency domain, that is along the imaginary axis of the Laplace domain, and contain the transcendental aerodynamics. So it becomes necessary to convert the frequency domain GAFs in the Laplace domain. The Laplace domain unsteady aerodynamics must be in a rational function so that they can be easily incorporated into the time domain state space equations of the aeroelastic system. And the technique employed in the ASE module of ZAERO for this conversion is the rational function approximation. So let's review that. The use of RFA permits each element of the GAFs to be written as a rational function, that is, a ratio of polynomials. So the general expression of the RFA is given here in equation 1.3, where we have a Q tilde of S, which is the approximation, is given by this equation on the right-hand side. So S is the Laplace variable, A0 represents the aerodynamic stiffness, A1 represents the aerodynamic damping, and A2 represents the aerodynamic apparent mass of the unsteady aerodynamics. R here is a diagonal matrix which contains negative numbers defined as the aerodynamic lag roots to model the aerodynamic lag effects due to the unsteadiness of the flow. The RFA is essentially a least square fit technique that approximates the GAF matrices at several discrete reduced frequencies computed by the unsteady aerodynamic method, called the tabulated GAFs, by the expression shown in equation 1.3, such that our Q tilde of IK is approximately the right-hand side when you substitute IK in for S. And then our L here is 1 through NK, where NK is the number of reduced frequencies at which the GAF matrices are computed by the unsteady aerodynamic methods. Now, once this least square fit is accomplished, equation 1.3 is obtained by simply replacing IK by SL over V, where SL over V is equal to G plus IK, where G is the non-dimensional damping. This expands the unsteady aerodynamics from the imaginary axis, which is G equals 0, to the entire Laplace domain. Now the number of aerodynamic lag roots and their values are specified by user input, and the best number of aerodynamic lag roots should be determined by a trial and error procedure. Now note that both the number of lag roots and the values of those specific lag roots are specified by user input, which could potentially be a very large number of inputs. However, ZAERO provides an empirical equation to calculate the values of the aerodynamic lag states by default. So if you do not specify the values of those lag roots, you only specify the number of lag roots, ZAERO will calculate those values of the lag roots for you based on this equation. So nlag is the number of aerodynamic lag roots, and Kmax is the largest reduced frequency in the list of reduced frequencies at which the gaffs are computed. And this normally will give sufficient lag roots to where you can get good RFA, which approximates the results which match the frequency domain results pretty well. So you only need to try different numbers of lag roots. Additionally, what I've found, if you have an unusual list of reduced frequencies, for example, you're doing a gust analysis, which we haven't talked about yet, but if you're doing a gust analysis and your K max is a very high reduced frequency, for example 5 or 10, this empirical equation may not work as well. In that case, what I like to do is manually use this equation and plug in my own K max, usually 1. So if I have 5 lag roots, I'll plug 1 for K max into this equation and then calculate the 5 roots incrementing I from 1 to 5, and then n lag would be 5. And then those specific values that I calculate, I can specify in ZAERO, and that may give me better RFA approximation. So what's the rationale of this RFA approximation? The validity of replacing IK by SL over V for this transformation of Q of IK to Q tilde of S, where SL over V equals G plus IK, and G is the non-dimensional damping, is given here, where Q tilde of S is analytic in the entire Laplace domain except at the negative real axis where a branch cut is located. Now, based on analytic continuation, Q of IK can be extended analytically from the positive imaginary axis to the entire Laplace domain, which is Q tilde of S. And why does the rational function approximation contain the aerodynamic lags? The aerodynamic lags are, in this approximation, are the discrete poles at the negative real axis, and this approximates the branch cut along the negative real axis by a set of discrete poles. And the aerodynamic lags model the unsteadiness of the flow. Okay, next we'll talk about the least square fit procedure for the RFA. Equation 1.4 can be split into two equations, one for the real part and the other for the imaginary part. So taking the real part of Q tilde of IK gives us equation 1.6, and taking the imaginary part of Q tilde of IK gives us equation 1.7. Now in general, the least square fit procedure solves for A0, A1, A2, D, and E by minimizing this equation 1.8. So we're minimizing the sum of the squares of these epsilon values, where this epsilon of IJL is given by the difference of Q tilde of IK and Q of IK times some weighting factor, WIJL. So remember, Q of IK is the tabulated gaff value, and then Q tilde of IK is our approximated value using the RFA parameters. And this WIJL is the weighting factor assigned to each ij term of the gaff matrix. And we have two methods for achieving this least square fit incorporated in the ASE module of ZAERO. We have the Rogers method and the minimum state method. So first, let's talk about the Rogers method. The Rogers method treats the elements of E as free variables, while those in D are fixed and R has repeated roots. Thus, D and R have this following form, where if we specify 5, for example, lag roots in our input, each of these little R matrices would be 5 by 5, where the 5 values on the diagonal are the lag roots, and then this is repeated H number of times, where remember H is the number of structure modes. And then our D matrix here is an H by H identity matrix, and then we repeat that n lag number of times. So this equation indicates that the Rogers method results in the final size of the aerodynamic lag states equal to n lag, which is the user input, times nh, which is the number of modes, which could become very large if many structural modes are included in the aeroelastic system. And next we have the minimum state method. The minimum state method treats the elements in both D and E as free variables, and the matrix R does not contain repeated roots and only has the aerodynamic lag states in the diagonal terms. So if we have n lag equals 5, the final size of the R matrix is just a 5 by 5 matrix. Now the number of aerodynamic lag roots required by the minimum state method as a user input is usually larger than that in the Rogers method in order to achieve an accurate RFA. However, the resulting final size of the state space equations is much less in the minimum state method because the number of lag states in the minimum state method is only n lag, but in the Rogers method it's n lag times nh. So for example, if you have 30 structure modes using the Rogers method, you only may need an n lag between 2 and 5. But for the minimum state method, n lag would probably be somewhere between 5 and 8 for 30 modes. Now, because in the minimum state method both D and E are unknown, the least square procedure involved in the minimum state method is nonlinear. So with an initial given D, the nonlinear least square method procedure iterates between D and E until a specified maximum number of iterations is reached. So we start with a given D and then solve for E using that least square procedure, and then we use that E as the given and solve for D, and that's one iteration. And then you'll go through this iteration several times until D and E converge. Usually the accuracy of the minimum state method is less than the Rogers method. However, because the number of states resulting from the minimum state method is much less than the Rogers method, it is suitable for control system design. Now a little note here, we call this DED iteration nonlinear because you'll note that the elements in D and E basically have no physical meaning. They're just a mathematical solution to, we want to minimize the error, and this D and D iterate on each other. So if you slightly change the input, so for example, if you change the Mach number by just a little bit, which of course will give you a different ASE matrix, then your D and E matrices could change by an arbitrarily large amount, even though your input, the AIC matrix, would have changed very little. However, with the Rogers method, because it's only one iteration, or it's not even an iteration, you just fix, let's go back to the Rogers method, you fix D and solve for E. So it's a one-shot solution. If you change the AIC matrix by a little bit, then you can see that the when you solve for E, the elements will only change a little bit. And so the values in E have a little bit more of a physical meaning in the Rogers method. However, usually in most cases, the minimum state method is preferred because, as we said, the final number of states is much less. Okay, so now we'll talk about Karls' minimum state method for the RFA, which is the original minimum state method that we implemented. So Rogers' method is usually more accurate than the minimum state method, but Rogers' method leads to the size of matrix R being number of modes times number of lag roots, as we said, which could be too large for control law design. The minimum state method was first proposed by Karls, and Karls' minimum state method leads to the size of the R matrix to be only the number of lag roots, which is a small number of states for the ease of control law design. Now, the Karls' minimum state method is a nonlinear least square method. So it starts with an assumed D matrix, and then A0, A1, A2, and E can be calculated by performing the NH plus NC plus NG column by column least square solutions, where NH, NC, and NG are the number of structure modes, control surface modes, and gust columns. Now the calculated E is used to update A0, A1, A2, and D by performing NH row by row least square solutions. So this entire sequence of least square solutions form a DED iteration, which is repeated until the specified maximum number of iterations is reached. Now, using Karls' minimum state method, it's evident that the inclusion of QHC and or QHG affects the approximation solutions on QHH. In other words, when control surfaces are considered or the gust column is included, then the approximation matrices for the generalized aerodynamic forces, QHH, are different from the case when there is no control surface or gust considered. So now let's look at the stability boundary of a linear system with and without inputs. And of course, in theory, this must be invariant. So based on the assumption of linear theory, the stability boundary or the flutter boundary of a linear aeroelastic system with or without control surface or gust input must be the same. The stability boundary of the linear aeroelastic system can be determined from the eigenvalues of the system matrix AAE, which is given here. Now, since AAE only depends on the RFA for QHH, then the application of the RFA to QHH or to QHH, QHC, and QHG must give the same stability boundary. Thus, Karls' minimum state method violates the assumption of linear theory. So we'll do an example here using Karls' minimum state method. This is the flutter boundary of a generic advanced fighter aircraft, GAFA, and it's computed by Karls' minimum state method. Now the flutter boundary of the GAFA is computed by the Statespace approach using Karls' minimum state method. So on the left here we have a structure model, and then on the right is the aerodynamic model, and this is a standard ZAERO test case. Now the RFA is applied without control surfaces first, so Q of S is just equal to QHH of S, and then secondly we do with control surfaces, so Q of S is a combination of QHH and QHC. Now the flutter boundary with and without the inclusion of QHC computed by Karls' minimum state method are different, which violates the assumption of the linear aeroelastic systems. So our solid curves here are with the control surface, and then our dashed curves are without the control surface. So you can see that the flutter boundary here, which occurs on mode 2, is different with and without the control surface, which is not correct. So next, at Zona, we developed the modified minimum state method to correct this error. Now the modified minimum state approximation method performs the DED iterations towards QHH alone first. Thereafter, the additional columns in A0, A1, A2, and E, which correspond to QHC and QHG, are obtained by one more DE procedure to solve for the NC plus NG column by column least square solutions. Therefore, the RFA matrices of QHH is independent of the inclusion of QHC and or QHG. Now, the invariant flutter boundary of GAFA with and without control surfaces computed by the modified minimum state method is demonstrated in this figure below. And our two curves with and without control surfaces lie on top of each other, so you can't see the difference between them. So by default, in ZAERO, the modified minimum state method is used. However, if you want to, you can activate the original Karls' minimum state method in the input. For example, if you have an older version of ZAERO which didn't have the modified minimum state method and you want to match those results in the newer versions of ZAERO, you can do that. But of course, by default, we always recommend using the modified minimum state method. Next, we'll talk about the RFA constraints. Now, because of the least square fit, both the Rogers method and the minimum state method do not guarantee that the RFA results are the same as those tabulated gaps that are computed at a set of reduced frequencies by the unsteady aerodynamic method. However, you can apply up to 3 constraints to be imposed on the least square fit to have an exact match with the tabulated gaps. These 3 constraints are: 1, matching the steady aerodynamic stability derivatives. So the gaps at 0 reduced frequency contains the steady aerodynamic stability derivatives that provide the static aeroelastic effects. So if you impose A0 is equal to Q of IK equals 0, then the accuracy of the static aeroelastic effects can be ensured. Secondly, you can match the aerodynamic damping derivatives. The imaginary part of the gaps at a small reduced frequency contains the aerodynamic damping derivatives that, together with the steady aerodynamic stability derivatives, dominate the aeroelastic response at slow motion. Now, based on equation 1.7, this constraint can be satisfied by imposing equation 1.12, where we're matching the imaginary part of Q of IK over K. And then lastly, you can match the real part of the gaps at a non-zero reduced frequency. So sometimes it's desirable to match the gaps at a higher reduced frequency at which the anticipated flutter mechanism occurs. Now, based on equation 1.6, this can be achieved by imposing this constraint in equation 1.13, where we match the real part of Q of ik at some given reduced frequency. Now, it's extremely important to know that imposing constraints to the RFA always increases the overall error of the fit, and an overconstrained fit could cause unwanted wiggling in the resulting curve and lead to an inaccurate aeroelastic solution. Next, we have special treatment of the rigid body modes. So the modeling difficulties associated with the rigid body modes are one, the finite element code does not provide pure rigid body modes with exact zero frequency. Next, the associated aerodynamic coefficients do not match the flight mechanics stability derivatives. And finally, some rigid body routes are theoretically zero, which are neutral stability. However, numerical noise in the RFA procedure might cause a small positive real part of the eigenvalue to develop, which could lead to unrealistic instability. So ZAERO provides various options to deal with these difficulties. One, we have the support option in the assign FEM executive control command. This transforms the finite element rigid body modes to body axis modes of pure translations and rotations about a chosen reference point in the ARO-Z bulk data card. This may be used to generate pure kinematic rigid body modes, and we always recommend using this option. Next, the RBQHH bulk data card replaces the gaps of the rigid body modes by wind tunnel or CFD calculated aerodynamic stability derivatives. So this updates the gaps. So this would affect your normal flutter solution in ZAERO. And then similarly to the RBQHH, we have the min-IMP and min-IMP1 bulk data cards. These replace the terms in the approximation matrices A0, A1, and A2 by user-supplied coefficients. So using these cards, it can be proven that the rigid body dynamics computed by the state space equation when elastic modes are removed can match those computed by the flight dynamic model. So if you're doing an ASE analysis, I'd recommend using both the RBQHH card and the min-IMP1 bulk data card to update the aerodynamic stability derivatives with those that you have measured either by wind tunnel data or calculated by CFD. The RBQHH will update the gaps, which will affect the RFA approximation. However, once you go through the approximation process, you're not guaranteed to recover those exact stability derivatives. So using the min-IMP1 bulk data card allows you to simply replace those terms in the A0, A1, and A2 matrices by those measured values to give you back exactly the stability derivatives that you know are correct. Lastly, we have the RB-Red bulk data card rigid body reduction. This modifies the rigid body columns in A0 and A1 to enforce up to 6 zero routes. So one at K equals 0, the fore aft, side translational, plunge, and roll modes produce zero aerodynamic force, which leads to 4 zero columns in A0 and 4 zero eigenvalues. At a very small reduced frequency value, the imaginary parts of GAF due to the plunge and side translational rigid body modes are proportional to the real parts of the GAFs due to pitch and yaw rigid body modes at K equals 0. Thus, those two columns in the A0 and A1 matrix are proportional, which leads to 2 zero eigenvalues. So if there are 6 rigid body modes, the eigenvalues of the ASE model must have 6 zero eigenvalues. So the rigid body reduction RB-Red card can be used whether or not you decide to use the min-IMP1 bulk data card, and then you can also use both of these cards together. So I would always recommend using the rigid body reduction card to enforce those zero eigenvalues, and then if you have measured aerodynamic stability derivatives available to you, I would recommend using both the RBQHH and the min-IMP1 bulk data cards to input those stability derivatives. And then lastly, we always recommend, if you have rigid body modes, to use the support option in the Assign FEM card. So let's talk about the transformation of the rigid body modes to airframe states by the support entry in the Assign FEM card. So the objective of the support entry is to transform the rigid body modes from the principal axis to the body axis. The generalized coordinates xi can further be divided into two parts: the generalized coordinates of the rigid body modes xq and the generalized coordinates of the elastic modes xe. In general, there are 6 generalized coordinates of the rigid body modes of a free structure. So q1, q2, q3, q4, q5, and q6. The rigid body modes computed by the structural finite element analysis are usually defined in the principal axes, so they first must be transformed into the body axis. For 6 R-set degrees of freedom, one can define a 6x6 matrix RP containing the 6 rigid body modes in the principal axes, and a 6x6 matrix RB containing the 6 rigid body modes in the body axes. Now, once RP and RB are obtained, the transformation from the principal axes to the body axes is just xq equals RP inverse times RB times XR, where XR is TX, TY, TZ, and RX, RY, and RZ. This transformation is accomplished by specifying support equals minus 1, 2, 3, 4, 5, 6 in the Assign FEM executive control command. And the rotation center of the rigid body modes in the body axis is defined by the entries ref x, ref y, and ref z in the ZAERO Z bulk data card. The aerodynamic stability derivatives of the rigid body modes are computed in the body axis so that they can be replaced by the wind tunnel data. Next, we have the aeroelastic state space equations. So with the RFA in hand, the state space equations of the aeroelastic system can be readily formed. So first, the matrices A0, A1, and A2 and E can be further column partitioned into 2 sets of matrices. One is due to the structure modes and the other due to control surface kinematic modes. So A is broken up into AHH and AHC, and then E is broken up into EH and EC. Next, to facilitate the state space formulation, it's convenient to define an augmenting aerodynamic state vector, XA, given in equation 1.15. Now we can substitute equations 1.15 and 1.3 into equation 1.1 to give us equation 1.16. So on the left-hand side, we have the structure terms, and then on the right-hand side, we have the aerodynamic terms. Next, we define an aeroelastic state vector XAE, which is made up of xc, xc dot, and xa. Now, equation 1.16 on the previous slide can be converted into the state space equations, where x dot ae is simply ax plus bu, where our u is delta, delta dot, and delta double dot, and then aae and bae are given in equations 1.20 and 1.21. We have a new term here, m bar, and m bar is given in equation 1.22. Now the number of states in this equation is 2 times the number of modes plus the number of lag states specified in the input for the minimum state method. And then for the Rogers method, it's 2 times the number of modes plus the number of modes times n lag. Next, we'll look at the outputs available of the aeroelastic model. So in general, the state space equations for the sensors can be written as simply y equals cx plus du. And there are various types of sensors that can be selected for output, including displacements, velocities, accelerations, grid point force, and sectional loads. So first we have displacement sensors. So the YAE is just phi h times XAE plus phi c times UAE, where the phi h and phi c I are the modal displacement of the natural modes and control surface kinematic modes at that particular sensor location, respectively. And those are just multiplied by xc and delta. Next, we have velocity sensors. So the phi and phi are instead multiplied by c dot and delta dot. And then next, the acceleration sensor. Ideally, you'd like to multiply phi times c double dot and phi by delta double dot. Now, delta double dot is available to us because it's an input. However, c double dot is not available as a state. However, if we go back to this slide here, we can see that c double dot is this middle row. So c double dot is this term times c plus this term times c dot plus this term times xa plus this term times delta plus this term times delta dot plus this term times delta double dot. And that equals c double dot. So if we take phi and multiply by all of that, that gives us the final output equation for the acceleration sensor. Next, we have the grid point force sensor, which is just kghi times c. So kgh is kgg times phi, and kgg is the g-set stiffness matrix. So in this particular instance, this kgh must be imported into ZAERO because usually it's not available. And then next, the sectional load sensor. We have L, which is an integration matrix. So L times kgh gives us the integrated force over some component, which is our sectional load. Next, we'll review the actuator model present in ZAERO. Control surfaces are actuated by servo actuators that are modeled as dynamic systems relating the command control surface deflections delta, which are the actuator outputs, to the actuator control inputs UAC. The dynamic model of the actuator driving the ith control surface is specified by a transfer function of the form here, where delta over UAC is given by A3 over s cubed plus A1 times s squared plus A2 times s plus A3. Now, the order difference between the numerator and denominator in equation 1.29 is 3, which allows us to define delta, delta dot, and delta double dot to be defined as independent states in the actuator state space model, and thus they can be used directly as inputs into equation 1.29. In other words, the actuator model is strictly proper. The matrix D of the state space representation of that transfer function 1.29 is a ZAERO matrix. Now, if you want a higher order actuator to be modeled in ZAERO, this can be defined by connecting additional transfer functions in series as part of the control system model discussed below. Now, if we take a state space realization of the actuator dynamics of equation 1.29, that is given in equation 1.30. So this state space realization is what is used in ZAERO. And in general, the state space equations of more than one actuator can be expressed in equation 1.31, where we just build up the multiple actuators into one big actuator state space form there, x dot equals ax plus bu. Next, we'll look at the state space equations of the plant model. Now, because our x actuator equals UAE, then the actuator state space equations can be combined with the aeroelastic state space equations by defining a plant state vector xp, where xp is a combination of xae and x actuator. So breaking that up, we have c dot, xa, delta, delta dot, and delta double dot. These are our plant states. This leads to the plant state space equations. X dot is ax plus bu, and y equals cx, where all the subscripts are p, denoting the plant model. And then AP is just AAE, BAE, and A actuator. BP is ZAERO and B actuator, and then CP is the combination of CAE and DAE. Next, we'll talk about the control system definitions. So the feedback control system relates the ASE plant outputs, which are sensors, to actuator inputs. A control system in ZAERO is constructed from elements of three types. We have CISO elements represented by CISO transfer functions. You can have MIMO elements represented by MIMO state space equations, and then junction elements, which are zero order MIMO elements y equals du. And two types of connections are used to link the control elements as well as the plant inputs and outputs. First, fixed connections have a unit gain, and closing of the fixed connections leads to the vehicle model, which contains the inputs and outputs of all of the control elements. And the next, gains of the variable gain connections are defined by the user. The CISO control gain and phase margins, as well as the MIMO control margins, are computed for the gain connections. And control sensitivities are calculated with respect to the variable gains. Closing of the gain connections leads to the closed loop model. If you have required external inputs and outputs of the closed loop model, they can be assigned by the user. And then lastly, the aeroelastic model, the plant model, the vehicle model, and the closed loop state space models can all be exported to data files for control system design or analysis in other software packages, for example, MATLAB. So let's review the different control elements. CISO control elements are defined by a proper transfer function. MIMO control elements are defined by a state space representation, and then junction control elements are a zero order MIMO control element y equals du. And the overall control system is constructed as an interconnection of the control elements and variable gains, which leads to the control system state space model. X dot is ax plus bu, and y is cx plus du, and our subscript here is c, denoting the control system state space model. So now we'll finally build up the vehicle model. The vehicle model combines the plant model and the control system model through the fixed and variable gain connections. So this is details of how ZAERO internally builds up the vehicle model. This isn't as important to understand, but we give it here for completeness. Conceptually, you're just taking the plant model and you're taking the control system model and then connecting the two through your fixed connections and variable gain connections. So the system with the fixed connections closed but variable gain connections open is referred to as the gain open system. And the fixed connections are specified here in equation 1.40. And now we can substitute equation 1.40 into equation 1.39, where we've partitioned out everything as shown to make it easy to apply this feedback here. So this yields the gain open vehicle equations in 1.41. And then our AV, BV, CV, and DV are given here in equations 1.42. And then the figure on the right here shows the interconnection of the models. And then lastly, we create the closed loop system from the vehicle model. So now we take the input vector UV, relate that to the output vector YV via the gain matrix GV in equation 1.43. And splitting the terms up, we get equation 1.44. So GPP here represents the direct connection through a variable gain from the plant, system, sensors, and actuators. GCC are the control system internal variable gains. And then GCP and GPC are the variable gains specified in the inputs and outputs, respectively, of the control system, that is, gains on the sensors and to the actuators. Now, substituting equation 1.43 into 1.42 yields the closed loop ASE equations of motion. X dot V is A bar V times XV, where A bar V is given here in equation 1.46. Now the inverse shown here in equation 1.46, I minus dV times GV, exists assuming that the feedback given by equation 1.43 is well posed. And just based on the modeling restrictions in ZAERO, this assumption does always hold. So now we'll talk about how ZAERO does the ASE stability analysis. The damping and frequency of the ASE system can be computed by performing the following eigenvalue analysis. So we take our AV, and from the previous slide, we have AV minus S times I times XV equals 0. The damping ratio, 2 gamma I, and the frequency, omega Fi of the ith state, are computed here in equation 1.48. So 2 gamma I is 2 times the real part of Si, and omega Fi simply equals the imaginary part of Si. And I varies from 1 to the number of total states. The eigenvalue analysis is performed at a set of air density and velocity pairs to yield the damping and frequency curves of each state. The ASE instability, or closed loop flutter, occurs at the flight condition where the damping curve crosses 0, whose corresponding frequency is the flutter frequency. The output of the ASE stability analysis are the VG and VF diagrams, which are very similar to the G method flutter analysis results. Next, we'll look at the CISO stability margins. The CISO stability analysis addresses the case of uncertainties and possible gain and phase variations in one element at a time. So GVIJ of the controller gain matrix GV. To evaluate the CISO margins, the loop connecting YVJ to UVI is opened, and then the gain and phase margins of the resulting open-close system are calculated using the standard procedures in ZAERO, and then output to the output file. The MIMO stability margins are defined with respect to uncertainties in the diagonal matrices Li and Lo. So Li is given as the diagonal of GLI times e to the j Li, where L is 1 to Ni, the number of inputs, and then Lo is given this equation, where k varies from 1 to No. Now for nominal conditions, GLI and GKO equal 1, and phi Li and phi KO equal 0. That is, Li and Lo are the identity matrices. To guarantee gain margin and phase margin at any input to the gain open vehicle, sufficient conditions should be fulfilled. And these conditions are taken from this paper, Control Law Synthesis and Stability Robustness Improvement using Constrained Optimization Techniques. So PV of S is CV times SI minus AV inverse times BV plus DV. And our sigma bar given here is the minimum singular value of the argument matrix. Now to get sufficient conditions for the output margins, GV times PV is simply replaced by PV times GV.